hit the wrong button. Good evening, everyone. Welcome to another live stream. How are you all doing tonight? I am very warm. It is currently 28.5 degrees in the garage studio. So we'll be sweating on making schematics today. Yes. The house is a nice 23.5, but the garage is less isolated. So I'm going to start with a drink, and I'm going to go for some nice, refreshing, there we go, Fanta Lemon Zero Sugar. What are you all drinking? Enjoying the AC a lot today. Yeah, we only have AC in the bedroom, but we have the floor cooling, which works well enough in the house, but here in the garage, not so much a thing. Oh no! Even the can is warm. Wait, why are we? Oh wait, okay. No. There, the lip actually didn't function. Flying home, but I knew you had to join. You're in the plane right now watching a YouTube video. What has the world come to? Do we have a screwdriver? We need to... Didn't we do this? I'm getting some deja vu here. Didn't we do this last time? Let me turn down the music. I distinctly remember something like this last time. But yeah. Uh-oh. Okay, maybe it's some lever action. No, wrong way around. Okay, maybe I'm just gonna leave this can. I'm gonna get a glass before I hurt myself. I'll be right back. Hold on. Now the question is, will it come out? Because it needs air, and the hole isn't that big. Quinn can opener, yes. Let's see. Yeah, I was afraid of that. Or maybe I can squeeze it out. There. Almost done. Okay, good enough. Why am I stuck? There. I'm gonna put this over there. Okay. So I have my drink now. All is good. Oh no, there's drink everywhere. There's drink on my mouse. Can't have sticky mouse. I don't like sticky mouse. Quinn Cola. No, this is a Quinn Lemon. Why is there an odd bar on the chat? Maybe I need to change it slightly. There. Okay, all good. Now I can have my drink. Cheers. Hey there, Greg. Hi to Janice and Malachi also. Hope you enjoy the stream. It's going to be another one of those boring finding parts and putting them in a schematic one, but, you know, we have to go through a few of these to get it a bit further than it is, you know. At some point it'll be done, but it'll take many, many, many hours. Will well see smoke. Maybe from me when I'm melting. Could be. for the many hours. Well, that's appreciated. You know, I normally do this alone, so it's fun doing it with an audience. It's a bit slower, but that's okay. We get to learn together. You're -2 for your 28. Holy. Yeah. Well, the garage never gets cold. It just gets very warm. Oh, I should open up the AI again. Because our bomb is still in there, I think. Let's see. Projects. Yeah, okay. Winter Down Under. Yeah. Let's see. Did it give us the bomb? Oh, it did in a CSV file. I don't need a CSV. Oh, okay. It also did so in a not CSV file. Yeah, because I wanted to check on the flyback converter. I'm already doing stream stuff. It's bad. It's not 15 yet, but let me sign in here. Oh, Greg. That's going to be... Yeah, it's 34 degrees outside here, so it's still colder inside, but not by much. That is a giant transformer. Do I need one this big? I don't think so. Well, we can look at that once we're actually doing the stream. Oh, it's warm here. I was in my nice living room where it was like 23.5. Well, mobile airco, the normal living spaces are fine normally, and the bedroom has AC. So, you know, generally it's fine, but just here in the garage it's super warm. And I already had a headache, so this is going well. A 5-way split for 4,000 bucks, that's not too bad. Yeah, the new house will have floor cooling again, and then AC in a few key locations, including the new studio. A small USB fan from Blokker. Yeah. I don't understand. Why does this have 8 legs, but then... Okay, click it away, don't look at it. There. Not yet so much. We have some preliminary drawings for the municipality and things like that. Once I have more visually and final stuff, I will make a video about it and show it. So, yeah. The cost of electricity, about 30 cents per kilowatt hour. Hey there, Dutch Maker. Yeah, the idea for the new home is to revive Project Quinergy and run it mostly off of solar and batteries. I'm going to put as much solar on there as I possibly can. And then about 75% of the year, I think, will run from the batteries, so that'd be good. We don't have any mods yet. I think they're all barbecuing or something. The batteries are currently collecting dust, yes. But they're not cycling either. So there is, in LFP batteries, there is a degradation in regards to age. So each year they'll degrade like 0.5%, even just because of age, not because of cycles. But even then, they're good for like 15 to 20 years or something like that. So I'm not too worried about that. Quinn home of the future. Well, I'm trying to make it very technological advanced. No, actually technically advanced, with a lot of my own systems and batteries and heat pumps and, you know. That's the good. The heaving gets here. What? Okay. About the same. We have to pay 60p a day charge, standing charge just for having electricity. Oh, okay. CEO is missing in action. Yeah. Maybe I got the day wrong. No, it's Friday. No, I got it right. Okay, now I'm going to move the chat again, but I'm going to do it differently than last time, because last time I kept forgetting the chat. So now I'm going to try and order it differently. There. Okay. And then we need this guy. We need this guy. Okay. Oh. Oh yeah, it's some dead after collecting dust for 5 years. Well, it's not been 5 years, but I recently checked their voltage. Now I know with LFP voltage doesn't say everything, but the ones I haven't used yet, they're still at like 3.25 or 3.3 volts or something like that. So I mean, I think they're fine. Yeah. The Nabukasa cloud service for Home Assistant, you mean? I subscribe to that. I don't really use it because I just use a VPN, but yeah. Your impending diagnosis. Yeah, I haven't gone through any official diagnoses and stuff like that, but I have some traits. Let's just keep it there. Some pre-stream secrets. No. Oh, it's 16. We're just going to start with the actual stream. How about that? So, what was it exactly? It is used for bridging some serve, but never. What are we talking about, Greg? Oh, you mean the Nabukasa Cloud? Well, just look it up what it is. But it's the cloud service for Home Assistant. Yeah. Anyway, let's see. We can do the display capture again. There. We have our Claude from last week, which told us the components we needed to use. I think that's still a good list. And one of the things I wanted to check on is... so wait, let me open up the... where did we put it? Desktop? Wall sensor panel. So let's get KiCad in here. Oh no, what was unable... Oh, okay, it opened it in the wrong version. Not sure why. Open with KiCad 10. Okay. And let's get the schematics. No, not on that window. Why are you doing everything over here? Okay. So last time we did the whole left side here. And now we're going to do the right side. So I wanted to double check one thing. We had the comp here. And I believe for the comp, it actually gave us different components than what the datasheet did. But I don't remember. Yeah, so it said 10K with a 22 NF and 47 PF. But then I said, no, I think you're wrong. And then it still wanted that. But if we looked into the data sheets, we could see that they used a very different comp value. Now, I don't remember what I ended up going with. I think I went with the datasheet value. So 22 NF and 1K. Let me look up the datasheets real quick. Do I have those here? I think so. Is it this one? Yeah, that's one of them. This one? That's the other one. Okay, so let's see what they used for comp on this one. Here, comp. They used not connected. Okay, and then 1K and 22 NF. Okay, and on this one, comp, they used 3K and 22 NF. And I think we decided to go with the 1K and not listen to Claude. We can ask him while we do other stuff. There. Oh no, right, that's right. Fable is currently not pulled back. We used Fable too much, and after the stream they cancelled Fable. Anyway, let's go back to the bomb. Because I wanted to look at this the flyback, what is it called? Transformer. And that is a big unit with like 5 legs on each side. And if we look at this here, it even has more legs for some reason. It's like 13.5 by 13 millimeters. That's quite a big unit. And I wanted to see if we could maybe get a smaller one. So the specifications for this are, I believe we needed 1 to 0.5 or 2 to 1 or something like that. So let's look at pulse transformers and let's see if we can find a ratio that is good enough. 0.47, 0.53, 0.5. No. 2 to 1. Okay. Okay, in stock. Okay, we only have 20 now. But let's sort by price. Here, something like this. It's actually SMD. And it looks a lot smaller. It is 7.7 by 6 points. Okay. Well, let's see if we can get the exact ratio. Yeah, because this is the humongous one there. 37 microhenries. Okay. Oh, okay. Very different values. Let's see if we can filter on... Oh. They only have one. I don't know what the microhenry should be, but the one it's selected is 37. Let's look in... no, not this one. This one. T1. Let's see what they used here. So 2 to 1 ratio. And then they use this one, which we couldn't find anything about. Oh, wait, okay. We could find something. No, no. Maybe? No. Okay, nothing there. Let's see if we can find this one. Here they use 55 microhenries. Okay. Yeah, okay. Let's see what these guys have. Oh, they only have the TWEP. Okay. So we need a 2 to 1 transformer of around 55 microhenries. But if we, especially if we look here at 2 to 1, oh, they have 3. Okay. Yeah, something like this is nicer, but then it's only 9.5 microhenries. These transformers, man, they are confusing to me. Let's see what Claude made of our comp network. Okay. It would work on a benchtop with resistive load and would be a poor choice for your actual board. Nothing catches fire, but it's the worst dampened of the 3. Okay. That actually makes sense. The large signal problem is the killer the same mechanism of flag with a 1K. The error. Right, so because we're going to use a lot less power, generally speaking, we end up with a lot less headroom in regards to signal to noise. Okay. Sure, okay, that makes sense. So it's basically saying don't use... so the 22 NF stays the same. It just tells us to use a different resistor. Okay, I think we can follow along with that. And if it doesn't work for some reason, we can always change that resistor. That's no problem. So let's make this a 10K. Still have the same weird bug. Okay. 10K, 22. But do I then also need the... Because it had a 470 PF over that, which I didn't want to use. Not sure why it does that. Chat. Where's chat? Chat's now blocked. Okay, here we go. Oh, the chat wasn't visible? Okay. Or the live stream? Continuing on no longer existing fail. Yeah, they really pulled it like an hour after my stream. I guess they thought like, oh man, if they start designing hardware with Fable, we need to stop them now. And the US government was like, no, what are they doing? Okay. Oh, later, Rich. Yeah, the non-available transformers. Yep. Yeah. Oh, you had to make a whiskey rum. Okay, I get. Sure, Philip, I get that. Okay, 10K plus 22 NF. We're gonna believe the. We're going to believe the AI this time. Yeah, we're looking for different transformers. Something like this would be nice. But... I just don't know if we can go from 55 to like 9.5 microhenries. Does just nobody build PoE circuits themselves? I mean... You believe in AI. Why is it so hard to build this? I would have figured it would be easier. Let's talk more to the AI. Can you see if more transformers are available that suit our needs from LCSC? The selected one is rather big. Oh, you can't walk in your garden yet. Oh. Yeah, I haven't worked with transformers before, so I'm trying to, you know... We could always still go non-isolated, but if we can make it work isolated for not too much money, I'd rather do that. But, I don't know. I would have figured it would be easier to find a transformer. Okay, I have my mouse on the charger, but that's charged now. Good. Good instinct. It's for the full 13 watts. Yeah, we don't need that. Exactly. Blah, blah, blah. Holding firm on the 2-to-1 ratio, since anything... Okay. Well, I know inductors, and inductors and transformers are basically related. But I haven't worked with a transformer before. Not like this. So, that's why we're trying to figure it out. Oh man, it's warm in here. It's hunting. Good. Then we can talk. It's 21 degrees there, Philip. Well, in the living room, it's 23 degrees. That's fine. But in my garage studio, it is still 28.5 degrees and warming up because I now have 3 screens on, 2 cameras, a computer that's streaming with a large video card and stuff. Most are the wrong input class, okay. Or the wrong ratio. Yes, that's what I thought too. It's doing work for us. That's good. Otherwise, we're just going to draw it and then see if we can pre-order the parts that are listed in the datasheet. Because, wait, why can't I click here? Uh-oh. What's going on? I can't click the window. I can't click anywhere anymore. What? My mouse isn't clicking on things. Hold on. Oh, okay. I had to hit Control and Alt, and now it's working again. Okay. Anyway, this one. Let's see. JLC PCB. Can I sign in here? I guess so. Parts manager. Let's get some JLC. Let's get this part. So it does know it. And I can... oh, they're 4 cents. That would be nice. I can't believe they're 4 cents. Minimum. I need to order a minimum of 444. I don't want to order 444. I mean, if they're 2 cents a piece, I guess I can. No, I don't think they're 2 cents a piece, though. And this is probably another big one, right? This is the one from the evaluation board, so how big is it? Ah, see, that's a lot. This is more of what I was looking for. This is the size I want. This is a good size. I don't want this giant giant thing here. That's way too big. That we don't need anything close to that. And even this is rated for the 12 watts or whatever. We don't need anything close to that either. And we don't have a lot of board space. Yeah, in this case, they are isolating transformers because you're basically passing the voltage from one coil to the other. But yeah, let's see what AI is saying. I scanned a complete set of transformers. There essentially is one general part spot. It's a real trade-off. Every other clean, same 30 meter. Okay. Here's the relevant field. Blah, blah, blah. Okay. So this one, oh my god, it's $4. Why? Yeah, the pulse is the one that actually moves the needle in size. 3 watt ceiling. 0.25 amps at 12. That's a bit low. Yeah, no, I don't want to go below 5 watts. Okay, so they basically LCSC does not have a suitable transformer. Brandon, if you know what you're doing and you use it as a helper, I think it can help. If you don't know what you're doing and it does make mistakes or calculation errors or judgment errors and all those other things, so sometimes you have to tell it no, but if you don't know that it did that, that's going to be a problem. So I wouldn't rely on it blindly in that sense. Yeah, no, we did. So the example transformer is this one. But there is very little to be found about that one. Do we have images? Oh, I guess we have some images. Oh, Where did this come from? I want this. Download? Oh, fuck off. Okay. Where did this come from? The Sunlord datasheet. We're going to try and find this datasheet here. So this is the TWS datasheet. Okay. Maybe we can just find the product. Coils and inductors. Transformers. There we go. Okay. Oh, okay. That's sorry it's so small. If I make it bigger, it suddenly explodes. There. So we want a TWEP, right? So the one in the datasheet is a TWPEP. So let's select TWP. Okay, so they have for power line or current sense transformer for current and overcurrent, wire wound type for power line. I think we need this one. Datasheet. Yes. Okay. So let's find out what they used here. They selected a this guy. Can we find that in this datasheet? Yes. Oh, look at that. Okay, so the TWEP 999B3000T. But how big is it? 500 kilohertz. So we'll probably have to decode the product number. Let's go to the top. Okay, T is a transformer. And then 2 is a wire. Okay. 3 is for power. And we do need for power. So that's good. 4 is EEEP. Don't know what that means. Okay. Moving on. And then we have our name here, so we have the EPs, and then we have 09. The bobbin size of the pin there. Okay, don't know what that is. Okay, 8. Oh wait, 5 and 6 are here. What? So 1, 2, and 3, 4, 5. Why is 5 here and not here? That is confusing as hell. The core size. Okay. So ours is 09, and then we have the bobbin pin that is also 09, and then 7 is here. The product height, okay, it's also 09 in our case, so 9 millimeters, and then 9 is here. Number of coils, B. Makes no sense. Design code, okay. So we have A and B. Okay, core type EP. Yes. 9. So it's 9 millimeters. Okay. Sorry, just trying to follow the chat. Feed the datasheet to Claude and let it summarize the part. We're going full AI, baby. Okay. There, let's feed it here. I should actually put it in the project, but okay. No, I should put it in the project. Projects, wall panel sensor. Where's the documents here? Project knowledge. Good. Okay, so now it's indexing it in the project. Let's go back to the chat. Let's delete it here. I'm looking at the transformer. Can you decode from the datasheet how well, it fits our project and its physical dimensions basically tell me its specs human readable. Why does it scroll up a bunch? I didn't ask for that. Full AI, baby. Anyway, let's see if we can find out more in this datasheet. Or maybe over here. For signal for power line. Okay, we also have a max 3 watts. Okay, so max 3 watts, the RTSB series. 3 watts is a bit, you know, it's on the edge. But yeah. These are 9 by 7 by 11 to... Okay, so the smallest one is 9 by 7 by 11. So is this then... So this is 16. Yeah, I can imagine this being 9. If this is 16, that makes sense. Okay. So this is probably 9 by 7. But that's already a lot smaller than the one LCSC has. Unobtainable! You've got a datasheet in the project, really? Yeah, if you're working with Claude, it's better to put the datasheets in a project than to dump it in the chat, because otherwise you run into limitations real quick. Tells us a lot. So it's a transformer wire-wound power EP core 09 9mm ADIM. Okay, pin dimension, direction, height, 3 windings, design code. So it's EP9 core, 9 by 9 by 9 millimeters. Okay. It's notably smaller than the EP13. Yes. And now the question is, do they maybe have smaller transformers? PCB planar transformers. What does that do? Oh, they're huge. Okay. No, I guess we do. Later, Dutch maker. So they have EP9, 12, 13, 20, 25. Okay. But the closest one is the EP9, the TWEP. Not our exact 090999. Our parts electrical specs. Okay. So the AI is hunting is reading, interpreting the datasheet. Still 5 volt, okay. So I guess they don't have smaller than 9mm. I can't imagine that though. Because we don't need that much power, right? If we could get 5, maybe 6 watts, that's like an amp at 5 volt. We don't even need near that. So, you know, I'd prefer something smaller, but how do we find that? So if we look here, let's clear our filter. Yeah, it's very warm today, Savak. Just trying something like this would be nice. Degent. But they only make power transformers, okay. Or at least on LCSC. Yeah, but they don't have anything near what we'd like. We can try and look up the brand. Doubt they have a website though. Can't write. Now I'm getting Transformers. No! Transformer Land. No. Okay. Yeah, that's hopeless. Can't look for the word transformer. Oh, XR also makes transformers. XR, I use a lot of inductors from XR. Transformers. Power transformers? Pulse? Oh, okay. LCSC broke. Uh-oh. Yep. Oh, okay. It's fixed. 2 to 1. One option. Yeah, no. Okay, pulse transformers. Nope. Okay, let's see what AI's figured out. I'd really like something smaller. Wire wound transformers. EP6. Does that exist? Highly compact surface. Yeah, that's exactly what I want. Good. Who makes these? Borns. Borns is very expensive sometimes. Okay, the Borns transformer datasheet. There, let's see. What does this do? For ultrasonic sensors? What? No. Pulse. There we go. Okay, so they have the EP10, EP13. Active cell balancer circuit. Oh, okay. I'm just trying to find if EP6 like exists. Let's see where AI is so far. Yeah, okay, we already read this. Okay, so it's 555. Okay, leakage. Ratio 2 to 1. Okay. Sure, okay, so it gives us all the specs from the datasheet. It's meaningfully smaller, but 5 watt peak, that's fine. Again, it scrolls up. I don't know. So we're still trying to find the right transformer. I can use the one in the datasheet, I think, because it is a part. Oh, if it's a part, can I look at... Oh, they don't actually list the manufacturer. Wait, can I find this on LCSC? No, damn it. Okay. I was hoping I could find a different compatible one, and then, yeah, I don't want to order 444. That's just insane. And it's in new arrivals. Do they have more TWEPs? TWEP in new arrivals. No. What? DWPEP. Oh. Did I spell it correctly now? Yes. Oh, okay, so they got more. Of course, we don't. They're all 09s. Okay, so they don't have smaller ones. Okay. This one actually says it's from Sunlord. Okay. Let's see if JLC PCB maybe has more in their catalog than LCSC does. That can happen. 2-to-1. Okay, so they have 15 2-to-1s. Hold on, let me clear this. Two to 1. 8. Okay. Interesting. What's this? Oh, no, I don't want to do that. Oh, 14 by... What? It's huge. Okay. Nope. They're all really big. Damn it. Let's see what AI found. Below EP7, it gets very hard. Okay. Then can we find some EP7s? Uh-huh. 3 watts. 6 watts. Okay. Oh, EFD 20. Yeah, okay. Then we go to EP7, but... Okay. What's this? A pulse, blah, blah, blah. Yeah, but is this suitable for our needs? Yeah, okay, that's fine. If you want something, the pulse. Is that the one we looked at? Yeah. Okay, but then we need it in a configuration that's not listed. Ah! Slightly intoxicated. Yeah. Yeah, I don't know where to go from here. That's the problem. We kind of want a smaller inductor because the current one is just huge and not really. We don't need near 12 watts or whatever like that. It's going to take a huge amount of board space. So we want something with a smaller transformer. Or we want a smaller transformer. But it seems we're unable to find one in stock at any parts vendor I like to use. Let's see if we can find more about this. Low power PoE transformers from... Okay, let's go there. Products. You'd think this was more commonplace, right? These items. I don't want chat, I want products. Transformers and inductors. Yes, that's why we're here. Products. Ah, okay. PoE transformer, EP7 series. Good. Scroll up and down to... Okay. We want 12 volt out. Okay. Oh, they got 2. Okay, they got none of those. So they have a 10 watt and a 12 watt. Okay. PCB layout. Is this the data sheet? Yes. Okay. So this one is 10. It's still 10. It's funny how you can go, I don't know about this topic, can anyone help me? And 2 years later, you're still searching how it actually works. I don't know. I have a grasp of how it works, but we just need to find the right part. So, what do they have in 5 watts? But isn't this bigger? Yeah, this one's bigger, so that doesn't make sense. Okay, so they have 3 12 volt parts. With the sizing model and specs, yeah, it's just hard to find all the right parts to all fit together perfectly for the exact need you have at that moment. In this case, I just want something smaller. I didn't think that would be such an issue. Yeah, this guy. These also don't have them. 12 volt, 5 watt data sheet. It's not on the website. Okay, so we're stuck with a large transformer. If we're stuck with that anyway, we might as well go back to our to this guy, because this guy, in theory, is this guy, right? I'm okay with this size. This size is okay. So this is an S210406. Yeah, I don't think we're going to find that. Okay. But in theory, These both say that they use the same inductor, S210406, S210408. Okay, but that's probably the production date. No, this is probably production date. Anyway, in theory, that is this inductor. This one here. And what we'll have to do, or what I will have to do, is I will have to source those outside of LCSC and then have them sent to JLC PCB and buy like, I don't know, 20 or 30 to do the prototyping. But I think that is the only option to go for, because this one we know isn't too big, right? This is okay in regards to size and what we need. And it's verified by their own evaluation boards. So yeah. Now we just need to get the symbol and footprint for those. So let's see if we can do that. I think so. If we copy this JLC PCB number and we go to our KiCad and we go to our PCB. One moment, it's opening on the wrong window again. And then we use our parts importer, import GUI. And we want to import. It's not there. Okay. Copy. What do you mean? Okay, I have to put it in a notepad and paste it again. There. Let's see if we can import that. Okay, it created a footprint and a symbol. Okay, so that's good because that's what we needed. So now we can close the PCB editor again, and we can go back here. We can go here, and we should have a how do we call it? Go away. KiCad import. I'm going to call this Q import. That's what I normally do. There. Okay. Why is these not closed? Okay. Nope, close it. Q import. And here we have our transformer. Or at least a symbol to work with, or to start with. And then we also have a footprint for that. So we can take a look at how big that is once we do the PCB work. Big flashes? I don't have any big flashes function here. Where are you seeing big flashes? Or is it... Did I miss some thunder, or... Oh, okay, now I get it. You are seeing thunder. I was confused. I'm like, is my computer showing flashes, or what's going on? I'm in Brabant. Yeah, that's right. Or you're near The Hague. Okay, yeah, that's far enough away to not be able to see them here. There. Okay, sure. Yeah. Okay. So now let's go back to this guy. Let's close some tabs here because we've decided to go with the transformer in the evaluation board, hoping I can actually source them. But we'll figure that out sometime later. Let's take a look at the schematic. So, let's work on VBus. They want a 2.2 UF, 2.2 UF, and then a 10 NF. Okay. And they have a 2512 transformer here. Or, sorry, transformer, inductor. And I think this is a 10 UF, but let's verify that. That is L1. L1 is a 10 microhenry 2512 1. Okay, sure. Okay, it's a huge DCR. Okay, that's fine then. It only needs 1.7 amps. Okay, that I can find easily. And then C1A. What voltage is that? 100 volts. Really? Wasn't VBus much lower? Let's close all of these. I don't care about this anymore. I thought VBus was much lower voltage. I don't remember. But it's connected to SW using the same coil, so probably... Let's see what they used here. They also used 10 microhenries and C1. Yeah, also 100 volts. Okay. Well, sure. Okay, we can do that. That's no problem. So let's work on VBus first, like I said. I think this one is the clearest. We have two VBus pins. We tie them together and then a capacitor to ground. Okay. So do we have any fun capacitor here? Sure. Let's borrow this one. We're tying the VBus together. We're going to move VBus up here. So like that. This one was a 2.2 UF 100 volt. We'll do the part selection later. I don't think we did. Yeah, okay, we did do. Did we do the sizing? No, we didn't do the sizing everywhere, I think. The footprints. No, we'll do the footprints later. Okay. You move away. So this is a... Where's ground? Ground's here. Then we need an inductor. So that's an L small. And this... Oh, I hit edit. Nothing appeared. Wrong window. Okay, value will be 10 microhenries. There. Let's select it on LCSC so we can add it. Let's go for 10 microhenries, whatever. I just need the fixed inductor category. And then I also always have to clear the search term, because then I have to select it here again. 10 microhenry. And they went with a 2512. That is a good size, because we can get that in molded. Oh, right. That is the different naming for... Yeah, okay, we can find it here. Nah, but we'll just look at it here. We need about 2 amp saturation current. Oh, I'm hearing drops. I think the thunderstorm reached us anyway. In stock, okay. Cheapest. So I don't like using these anymore. I like using molded inductors, as I call them. So this guy. This is also this is a 2520. That's fine, but these are like a few cents. 1.4 amp, 1.8 saturation. It's a bit low. What did they have again? L1. Oh, they had 1.7 amp saturation. All right, that's fine then. Yeah, so this should be good. What? What do you mean? Try again. Okay. So this is 330, 1.4 amp. Feels a bit low. Let me do some other stuff. Let's clear this. I want a bit more saturation. I don't know why, but 1.7 till 3. Yeah. Let's see if we can find a slightly better one in the same package. Nope, don't think those exist. All right. Fine. All good. We'll use the cheapest one. Where is it? Here it is. LCSC is slow today. So we have a 1.4 with 1.8 saturation, I believe. Yep, okay, that should be fine. 330. That matches the evaluation board pretty well. So we're going to go here. We're going to go. Oh, why? Add LCSC there, so we know which. Oh, we can select the footprint too. Oh, okay. Oh god, we need to find the inductor. Inductor. Yeah, I believe they're over here. Yeah. 25. So this is a 2520. Yeah. 2520. I believe that is correct. With 2.5 by 2 millimeters. And the one we selected is, doesn't say, but it's 2.5 by 20 by 12. So 2.5 by 2 by 1.2. Oh, we have a 12 here. Okay. So that is the correct size. Okay. Then going back to the data sheet, we need another 2.2 microfarad capacitor. So we can just copy this one. There. I'm just going to do it like that. Okay. And then they have a 10 nanofarad capacitor. Okay. That's to filter out some high frequency noise and stuff like that. Okay, And let's see, then we couple to the transformer, but the one thing this doesn't really show is all the different windings. Let's see if the other one does. No. Because if we look at the transformer we imported, we see that we have lots of terminals, but I guess we need to treat 1 and 2 as the same and 3 and 4 is the same. Now we can try and verify that by the copper layout, and I think I remember from before that that is correct. Where is the copper layout? Here. Yeah, so they're treating pin 1 and 2 and pin oh no, 4 is isolated, 3 goes to this pin, 1 and 2 go here. Okay. And on the other side, this goes to ground. And this goes to these ports. But then how am I supposed to read that from the datasheet? Or from this circuit? Oh, I hear some cats running inside because they're probably getting wet. Not all of them, but the good ones do. The more complex ones function here. Yeah, so we know this. These two. But this is more guessing than knowing. So I don't actually like that. What the? Why would you do that? Wow. Okay. Okay. But then how do we know? So this is SW. No, wait. SNBR is connected to those same pins. Okay. SNBR seemingly has a capacitor, C4, which is a 50 volt. And what do these guys use? SNBR, same value. C4, also 50 volts. Okay. Why that one doesn't have to be 100 volts, I don't know. Because it's connected to the same legs, right? How does that make sense? Yeah, it doesn't make sense to me why these capacitors needs to be 100 volt, and then this one can be 50 volt. Because if it's swinging the same voltage as the V-bus, yeah, maybe. Okay, well, I mean, I'm not developing this circuit myself. We're just copying their circuit, so you should be able to assume they got it correct. So we're just gonna do that. I mean, yeah. Trust but verify. Well, we have two data sheets which basically say the same thing. We can look it up in the Let me look up the ice. No, wait, don't. MP. Let me get the datasheet real quick, and then we'll see in the datasheet what voltage that leg has. So we're talking the SN... Hello? Why is this datasheet so difficult? Jeez. Well, sure, but yeah, SNBR is connected to VBus, which is connected to that. Yeah, okay, that's what we have. Wow, this datasheet's slow. Okay. SNBR. Active clamp snubber capacitor connection pin. Connected to the drain of the internal... Okay. Doesn't tell me much. Okay, so the absolute maximum ratings for SNBR is 105 volts maximum. Okay. The discharge threshold before switching, 1.5 volt. Okay. Over voltage threshold. Okay. The SNBR voltage is almost equal to VBus. So then you'd say needs to be 100 volt capable. It's recommended to place a 4.7 microfarad capacitor on SNBR to clamp the transformer leakage inductance energy, sure. Otherwise the SWM may become too high. So it's limiting the maximum voltage of the switching node somehow. Okay, sure. If the SNBR exceeds 105 volt, stops all switching and enters hiccup mode. Okay, so SNBR can go up to 100 volts. Active clamp. Yeah, okay, we don't need all this. Okay, so basically what that tells me is we're not going to listen to them. And we're going to say this needs to be able to do 100 volts. Because if I interpret their datasheet somewhat, I don't know why they selected a 50 volt capable part, but as I see it, it can go up to 100 volts. So oh wow, Foxionaire. Okay, and it doesn't actually need to go here. So this one has it connected over here. Maybe because of the filter, right? Because this one has it also connected over here after the filter. But in the data sheet itself, they just connected directly. But that's probably because they don't have the inductor filter there. So let's follow the evaluation board schematic and connect it to this pin here. A big lightning fan. Oh, it's okay. I like a good lightning storm and some rain. Okay, so we got the SNRB. I'm actually going to do something here. I'm going to, I don't know, some engineers now probably screaming at me. But I like this better. Oh, I do hear some rumbling here now. Oh, near the coast. Oh, yeah. Oh, yeah, it's definitely rumbling here. And I already heard some rain a bit ago, so we'll see. Now, if we follow the datasheet more, this one is unconnected. And the other leg, oh, this is EP7. We couldn't find EP7. We wanted EP7. Anyway, this is connected to SW. But it has a few more components. It has a 0.22 microfarad, yeah. C6. 10 volt. 10 volt? Well, we got a flash. We got a flash. Why pin 18 and 19? Probably for more current handling, right? So if they use more pins, it's probably because they need more current out of that. Oh, okay. Lots of rumbling and flashing here now. Can you guys hear that? Let me turn off the music. Okay, let's leave the music off for a little bit. Right, SW has, but why are those, why is my keyboard not working? There, 10 volt. So SW actually doesn't have a high voltage on there. What is SW again? I'd say that's the switching node, SW. I mean, huh? Drain of the converter's main switching MOSFET. But we're generating 12 volts. Your micro... No, maybe. Don't know. Drain of the converter's main switching MOSFET. But then, wouldn't that... We're outputting 12 volts. So why use a 10 volt... And why is it 0603? Such unexplained things. Let's see. R1. Okay, that's a standard resistor. C7, C8. Where's C7? Oh, here. Okay, yeah, that's okay. That's okay, that I can understand. Yeah, okay, we're not going to follow the datasheet again. We need the 0.22 UF, that's fine. Let's copy this guy. Where does this go? Oh, this goes to BST, okay. Then I'm going to do a little bit of trickery here. It's not pretty, but it'll work. And I'm going to say 0.22 UF 50 volt. It doesn't really matter because with that low value, we can probably get an 0603 or even an 0402 at 50 volt. No, go here. And we also need a resistor, 240 kilo ohms to feedback. Let's borrow a resistor. $240 kilo ohms. Should I use a small or a large K? I don't remember. Small. 50 volts. And we can use an 0402 for that, unless there's like a lot of current, but a feedback resistor generally doesn't have to handle a lot of current. So, yeah. So now we have all the pins here filled out. Good. So we can continue on the transformer. If you see here, we had the these connections we've made, this connection we've made, but we have 4 connections because this transformer probably has 4 pins. But if we look at the copper, we'll look at the copper of this one. There. We can see that these 2 pins, they're linked together. Okay, wait, you can't see my mouse. There. These 2 pins are linked together. This pin is linked here. That's what we did. And then this one is unconnected. So that's why I put an X here. So unconnected pins, you put an X there with this guy. This one is connected. So I think for the left side of the transformer, we're done. And then for the right side, we need some more stuff. We need a big diode. What is this? Okay, they have them. 760 millivolts at 3 amps. Okay. So this one is not too expensive. This one, oh, the Q. If there's a Q in the part number, that generally means there's rated for automotive. We don't really need that. It's not too expensive. 100 volts. Okay, it has a fair bit of dropout, but for what we were doing with it, it's probably going to be fine. Let's see what the other datasheet uses. Probably the same one, but... Is it the same one? No, they use a different one. PDS 510013. PDS 510013. Quindo approved, yes. Okay. So, oh, they're using a 5 amp version. Okay. Yeah, in our case, we're never going to use a lot more than a few watts. So we can just use the 3 amp version. Let's look at the datasheet real quick. Power DR5, sure. It's rated up to 100 volts. Yeah, why not? I think that's going to be fine. So we're going to add a diode, but on which pin? Okay, let's go here again. So they're joining again 2 pins, and the other pins are going to ground. Yeah, okay. So let's do that first. These are going to ground, but they're going to ground after the split, right? Because this is an isolation barrier, so this ground and this ground isn't connected. Yeah, generally automotive is a bit higher rated, so it can do a bit higher temperatures and it's more tested, but you're going to pay for that, so they are generally a bit more expensive. So what I just did is wrong. We can't use the same ground on this side and on this side. So this shouldn't be ground, but we're going to use a different symbol for that. So if we look up ground, we can find different grounds. We can do ground 2. Or ground 1, I guess. Ground power. Actually, I want to do it differently. This is going to be ground. And the ground on this side, we're going to replace. because right, we need to make this separation, but the ground we're going to use on everything other and on all the other PCB parts is going to be this ground and not this ground. So they started calling it VSS, and I think we might need to copy that. So we're going to replace all these grounds with VSS. That's all connected. Okay. Power ground, analog ground. Yeah, since we use the one symbol, that's actually pretty easy. This can go actually there. Since we tied it all to the same net here, it's very easy to replace. So the ground on the left here, we're going to call VSS, right? Like they also did in the datasheet. And then after it goes through the transformer, it becomes actual ground we're going to use for the rest of the parts. So that way we don't have to remember to use a different ground. We can just use ground, basically. Okay. So we had the... Oh no. Okay, wrong. There. We needed the large diode. The transformer makes that separation, as you can see in the image. There's a gap here, and this box here is the transformer, right? So if we look at this version, they also have the stripe here in the middle. And if you look at that, you see the dots here. Those are the vias. You see that running straight under the transformer, and that gives you the separation. Okay. Right. We need a diode. Do we already have a diode? No. D small. Oh. And that's going to go between these two, because we saw these are linked together. And then we have the diode. Actually, we need to move this down a bit. Can we move this down a bit? Yeah, I think so. Why? Oh, man. Sorry, I'm not used to KiCad 10 yet. Normally, if I did this, it would fix these automatically. Okay, I'll fix them manually. We're going a bit high, so I want to move this down to here. And then delete this, delete this. That's correct, that's good. This is now wrong. There are rules for that, yes. You need a spark gap, or rather a clearance or a creepage distance. You can calculate that for the voltages involved, but even like 1 millimeter or something like that should be plenty. I think for 100 volt you need about 0.8 to a millimeter, but we can probably make it much larger than that. So is this still correct? I think so. Yes. Okay, good. So we have the diode here, but if we look in the datasheet, we had a 470 PF and a 10K. Let's see what they used for those. C11, 100 volts again, and a 1206 for the 10K, because it's 100 volts. That makes sense. Okay, that makes sense. Oh wait, R7. Is it R7? Oh, it's a 10 ohm. R7. 10 ohm? 10 ohm. Okay, I'm just blind. What did they use on here? 10 ohm, 47. Okay, that's good. I actually like this better. So we need a resistor. And that's going to be a... why is this so... 10, 100 volts. So it needs to be a 1206. And the reason is, the higher your voltage is, the larger the resistor needs to be. Yeah, that's kind of just a thing, right? So this also with capacitors and things like that. For the higher voltages, you need a bigger size. And a 470 PF. $100 volts. Okay, so we basically now just built this. And then we need our output capacitors. Let's go back to this guy. 2 times 22 microfarads and 1 times the 0.1. C2A, C2A. 25 volts. Okay, so this is our 12 volt output. So they doubled that voltage to 250805. That makes sense. That is fine. So one we can directly borrow here. No, we don't need 100 volts. Wait, we don't have any input capacitors? Oh. Anyway. Oh, those are over here. Yeah. Okay. So, just gonna borrow you here. This can be 25 volt because we have a 12 volt output. We'll figure out the sizes later, because I have my own way of doing that. And then we need one more. .1 UF, and these all go to ground. Yeah, okay, I'll do it like that. Yes, okay. This goes like that, and then I think we're ready to make our 12 volt and our they call it signal ground, but we just decided that was going to be ground. Yeah, here they also have the ground separation well labeled, so they call this power ground, and then after the transformer they call it signal ground. Fine, we'll just use our how do we call it, our VSS, because their VSS becomes power ground here. So we're just going to keep calling it VSS. That's fine. Okay. So we need a new power symbol. We're going to call that 12 volt. There. And in theory, that concludes our PUE circuit, except that they have some more things on there. And we're going to add those. they have these C12A, 12B, and 12C. And those are giant C12, 12, yeah. These are 1 NF 2000 volt. They are to provide some AC coupling between the two grounds, so that if some potential difference does occur, there is an AC coupling there so it can dissipate. 1808s, damn. Okay, let's see how the other one did that. C11, 12, and 13. Oh, I had to use the same ones. Sure, of course. Copy. Okay, and those go from power ground to signal ground. So those are the only ones that go in between the grounds. But as we can see here, they only fitted C12A, and the others are nowhere to be seen. So having 3 is a bit useless. So we're going to have 1. Okay, let's make that. So they want to go between ground, and in our case VSS, and we're going to have a capacitor. And that's going to be 1 NF 2000 volts. And we can already select the footprint for that, because we kind of know it needs to be an 1808 probably. So let's see, footprint, capacitor, SMD, 1808. Okay, there. And if you want to, if you're going to forget why this is later, what I usually do is I make a little box here. The box is ugly. We're going to call it ground coupling. There. Okay. Sorry. Yeah. Now, okay. This is going to provide an AC coupling between the two grounds, but not a DC coupling. So if you'd have a resistor there, or just a copper, bit of copper, that would give a DC coupling, because then voltage from one side can go to the other side. But capacitors don't allow DC to travel between them, but they do allow AC to travel between them. So if AC potential builds up at either side, they can basically flush through that AC coupling, but you still don't have a DC coupling, because you're using that transformer to get a DC isolation, right? And that's the whole reason why we have that transformer there, because we want DC isolation. So this way we keep the DC isolation while having an AC coupling. Okay, let me read. The output windings are connected in parallel, so 6 and 7 are one output and 7 and 8 are another. Oh. I now see indeed that this is 6 and 8 and 5 and 7. Interesting. Okay. So then, that's a good point. Yeah, so the problem is that we don't see the pins here. Okay. I'm not going to repeat that. So how do we know which pins are what? No. On the output here you have 2 grounds and 2 positives. So that, okay. Wait, there. 2 positives and 2 grounds. Here we have 2 inputs, 1 switching, so V-bus switching and then nothing. And I connected those as I saw them here. But if I now look at the symbol more closely, oh, this is 1 and 2, and this is 3 and 4. So I'd say this is 1, this is 2, this is 3, this is 4, right? But here, this is different. They have 6 and 8 and 5 and 7. So are these 6 and 8? That doesn't make sense. There's lots of YouTube videos you can follow, and then lots of experimentation, homies. Yeah, so these are likely wrong. There's lots of things, like Phil's lab is a good one, but you probably have to go back to some beginner tutorials. Oh, yeah, it's hard to recommend something. Five and six are ground, and 7 and 8 are positive. But how do we know that? So like that. Because depending on the numbering, if it's 1, 2, 3, 4, 5, 6, 7, 8, sorry, 1, 2, 3, 4, 5, 6, 7, 8, that makes sense. But if it's 1, 2, 3, 4, 5, 6, 7, 8. Let me look how they did it. Yeah. This just doesn't explain it well enough. Neither does this. And then why not connect these together? Why is this one floating? I don't get it either, Philip. It's a bit confusing to me. Because we're using the exact reference inductor transformer, right? We're using exactly this one. I have them tested in China, Don. So I can't really recommend anything here in the Netherlands. If you need equipment, go to Eleshop. Eleshop is a really nice shop. But other than that, yeah. Only two and only pins 2 and 3 are connected on the input. No. No, if we look here, we can see that there are 2 pins connected on the input, and then 1 pin here, and this one's floating. We're back to transformer issues again. Yeah, they just don't tell us. I agree this makes the most sense because it's likely labeled 1, 2, 3, 4, 5, 6, 7, 8. So 3 needs to be switch. Yeah. Maybe, Philip. Maybe. I don't know. According to the datasheet, pins 1 and 4 are not connecting to anything. Well, they didn't connect 4, but... Oh. Actually, that makes sense. Now, looking at this symbol better, this is connected to the input coil. And 1 and 4 are connected to nothing. So, if we look here, they're basically using these. And they probably just have copper here because it's convenient. Right? That makes sense. Okay, so 2 and 3 I can agree is probably right. This doesn't do anything, 1 doesn't do anything, but they just have some convenient copper there. Okay. But how are we supposed to know this? So they have 2 coils. Okay, let's ask AI. Maybe AI knows. On the transformer, we have 8 pins. Can you tell me which pins need to be connected to what? Did I save that datasheet? I don't think so. No, I did. Yeah. You have the datasheet for it in your project files. Let's see what AI makes of it. Hey, Draadstaal! We're blowing up transformers, technically speaking. But we've hit a snag, so now we're asking AI. Oh, these are linear magnetics, so they don't actually have a switch in there. It's a Keychron K2HE, And so it has the HE key switches. So you can actually set the activation point of each key if you wanted to. But I like them so much that I also have one of these at my main desk, the slightly larger model, but still. Later, Philip. Let's bring back the music. Because the AI is now working for us again. Not the most intelligent AI in the world like last time, because after the stream they banned it. It was too much. Waiting on the AI. I think the way we have it is correct. Now, I think the tip was very good. Because to generate a positive output, you kind of need a ground too. But yeah, it's a bit confusing. It's working. Okay. So I'm going to take a little shortcut. So I'm going to disable the display for a little bit. And I'm going to borrow a circuit from another board. But we'll work through it together. So don't worry about that. One moment.
Very much alike.
Okay. And we're back. I borrowed this circuit, which is a buck converter circuit. But we'll go through that and explain all the items that are there. So don't worry about that. 10 UF. I might have just spotted an error. Anyway, let's look up this this IC here. While the AI is working. It's a Diodes AP62300Z67, and it's a really tiny bugger, as you can see over here. It's a SOT 563, but it's a 4.2 volt to 18 volt input, 3 amp, low IQ synchronous buck converter. Now, what that means, we're going to have a 12 volt out, and we either want 5 volt or 3.3 volt. 12 volt falls right into the range of 4.2 to 18 volt, so that's good. 3 amp is way more than we need, so that's fine too. Low IQ means that it has low idle current, so that if you're not asking anything from it, it doesn't use a lot of power. And a synchronous buck converter means that it has a built-in high and low switch, basically. You can have asynchronous buck converters too, and those only have a built-in low switch, I think. Yeah. And they're generally a little bit less efficient. But yeah. But the good thing here is that they're like 7 cents. And again, what do you mean? Okay. My LCSC is randomly broken. Anyway, they're from Diodes, so they have a pretty good datasheet. And it's just, you know, very cheap, small, more than capable for what we need. And yeah, we can make our 3.3 or 5 volts from that, because the out can be 0.8 to 7 volts, or 12 volts falls straight into the input range. As I said, 3 amp continuous is fine. Oh, and the version I have selected here, is this a fixed version or not? They have fixed versions, I think. Oh no, this doesn't have fixed version. Okay, so this isn't a one where a variable version where you can choose the output. 750 kilohertz switching for V in 12 volt, V out 5 volt, all good. 83% efficient. Yeah, I don't care about that. This I do care about. It has some EMI reduction circuitry in there, so that's good. And yeah, it's generally pretty easy to use, and it's been set up. They have examples for 12 volt in, 5 volt out, or 12 volt in and 3.3 volt out. Exactly what we need, although we haven't determined yet what we need. Yeah, 10 UF. Oh, good. What did I use for C6? PST. Oh, okay, 100. Yeah. Let's see if AI came back already. This one. Okay, it's still working. AVM. The part is 3 windings on 6 of the 8 pins. Okay. Okay, two identical 12 volt secondaries. Ah, okay. Pins 1 to 4 appear in no winding measurement in the datasheet. Okay, so if we go back to KiCad and we look at here, 1 and 4 are not connected. So this one being connected is just because it was easier to route for them. Sure, that's fine. All 3 windings are accounted for by the 2, 3, 5, 6, 7, 8 pins, so they're mechanically anchor pads with no internal... okay, yeah. So 2 and 3, 2 goes to SW. That's not how we have it. And 3 goes to VBus. Nope. Okay. Let's see here. 6 goes to 12 volt out, and 8 goes to ground. 6 we have ground, 8 we have connected. Okay, it has everything. I think we can reverse those. And 5 and 7, same thing. Okay. Let me draw it into... Oh, okay, yeah. Let's wait for that and then ask if we can switch pin 2 and 3, 6 and 8, and 5 and 7. Otherwise, we just move it. I think since it's a coil, generally it won't matter where you start and end, right? But yeah. Later, Don. Where do you learn about components? Reading, a lot of reading, and then testing, and then reading again, interpreting the results, oscilloscopes. Yeah, It's experience you need to gain, so you need to do it. I'm thinking that since it's a coil, either side should work, but we'll ask AI in a minute. Let's go back to the data sheet for the DC-DC converter. We need a 3.3 microhenry inductor here for these examples, and these examples are exactly what we're doing, so that makes sense. Efficiency ratings, we're going to need like 100, 200 to 300, and so from 300 milliamps onward, we're right at the peak efficiency rating, so that's good. Because it's an ESP32P4 C6 and Ethernet, so we're going to use a few hundred milliamps. Yeah. So here we can see the regulations, what's it doing. One crucial thing, enable can be left floating, and that means that the device automatically enables once the voltage reaches the EN logic threshold, so we can just leave EN disconnected. But that's not always the case. Well, I can go through all of this, but I've kind of already done that for this circuit. But there is a mistake here. These two should be 22. That's correct. But I kind of wanted this one to be 0.1, I think. Not sure what happened there. So I'm going to borrow this one. There. Okay. So what we have here, we have the AP blah, blah, blah buck converter we just discussed. We have two 16... Okay, we need to change these because they're too low voltage, because the circuit I was using this on had 5 volt in, not 12 volt. For ceramic capacitors, you want to have they have a D rating, so if you have 5 volt, you kind of want a 16 volt capacitor, or if you have 12 volt in our new case, you kind of at least want 25 or even higher to make sure that the D rating isn't too high, because otherwise 10 microfarad isn't really going to be 10 microfarad. So we're going to change that to, we want at least 25, and then I think we want to go to 0805s. Because of the larger, the higher voltage, you also need, whoa, what? No. You also need a larger physical package, basically. Okay, delete that one. Copy this one. Okay, so we fixed our input capacitors. What? What do you mean? I can't... what? Go away! Okay, seemingly my spacing in my other editor is different. There, fixed it. So we have 20 microfarads of input capacitance with 25 volts. That's double of the 12 volts that's actually going to be there. And then we have a 0.1, that's a much smaller capacitance. That will go right up until on the V-in pin for some high frequency decoupling. And this is more bulk decoupling. Then following the datasheet, we have a 3.3 microhenry inductor. I already selected the exact model here, which should be plenty for our uses in this case too. 2.6 with 2.7 amp saturation. We're never even going to do an amp, so that's all good. Nice and small again. All good. We have our feedback capacitor here, and we have our BSD capacitor, our boost capacitor for the switch node. That's all been calculated already, so that can remain the same. Then we have these two resistors, and those determine the output voltage. So we need to decide if we need 3.3 volt or 5 volt, and I don't actually know anymore. So that's the last thing we'll do on this stream, and then at the start of the next stream we'll go over this buck convert again, because I just kind of pasted it in here. Oh, we're gonna rename this one, because currently this is for 3.3 volts. There. Okay, let's see what AI says, and then oh, look at that. It made a nice drawing for us. So 3 and 2, VBus and switch. In our case, however, it's 2 and 3. Yeah, so, okay. Sure. Oh, So here it coupled the inner ones on ground, and then the outer ones on 12 volt. Okay. Okay, so let's ask it if we can switch it around. Claude has somehow reversed the phasing. Yeah, it thinks it's right, but I'm not too sure about that. It looked at the dots though, so generally speaking, the dots would be correct. We have the dots on 8 and 7, 7 and 8. Okay, and on 3. So it did get the dots correctly. Okay. So does that then mean it's actually correct? Winding start, yeah. The dotted the orientation that makes the output during the flyback, yeah. This is what we had before. Okay, it's thinking about if that's going to work or not. This is what I use AI for mostly. The things I don't know either, it generally can find good knowledge on the internet and then parse that. I didn't actually tell it to go to the internet now, so it's just determining it on its own. But it's a good sparring partner for that kind of stuff generally. Looks like there might be some EMC implications. Yes, and it works identically because the transformer is symmetric and simultaneous flip of all its winding. Swapping the primary terminals reverses the primary phase. Swapping both secondary reverses by the same amount. So relative phasing that the flyback actually depends on is preserved. The rectifier sees reverse bias during the same energy, same 2-to-1. Okay, nothing in the operating point changes. One hard rule with which your proposal satisfies: you must flip everything together. Okay, flip only the primary and you'd break it. The diode would, yeah, okay, sure. So now we have what we actually have. So 2 is VBus. That is correct in our case. 3 is the primary, the switch. Where's switch? Yep, that's also correct in our case. And then 8 becomes 12 volt. Yep. And then 6 becomes ground. Yep. And then 7 becomes 12 volt. Yep. And then 5 becomes ground. Yep, okay. Paralleling still goes dot to dot. It just lands on the dotted pins now instead of the non-dotted. The thing worth your attention, wearing your EMC hat, this swap is electrically free but not necessarily EMC neutral. Okay. The end of each winding tied to the switching node is the high noisy end, and reversing the terminals changes which physical winding layout that noisy node drives, which shifts the common mode. Okay, your Y caps, I'm not using Y caps. Shunt the bulk. Okay, so winding. Okay, so if reversing is cleaner for you, go ahead. Okay, well, so it doesn't really know if this is going to influence EMC or EMI. That's basically what it's saying. But if we look in the EVM datasheet, so this evaluation board datasheet, I believe they have EMC radiated emission results in there, right? These are the radiated emission results of this EVM, where they have it connected this way with this transformer. So I'm safe in assuming, I think, that if we use the same transformer and their same layout, which we copied, right? We should be good EMI and EMC wise, right? So, yeah. But that's generally how I like to use AI. It basically confirmed what we were thinking, but it just gives a little bit more confidence without losing the subject or not knowing what we're talking about completely. It makes sense in what it says, and yeah, okay. It just doesn't really know about the EMC EMI thing, but we have another verification source for that. So, yeah. So that basically concludes our PUE power sheet here. It's not really pretty right now. Let's move this down. Oh god, can I move it now? Is this gonna work? Worked okay. That's already a bit better. Oh, did we not tell which diode this should be? A PDS. I'm just gonna name it there. Okay. Yeah. So this generates our 12 volt from our input, and then we don't have a symbol here. This one takes our 12 volt in and makes it 3.3 volt, which is, I think, what we're going to need for most of the circuit. But I haven't actually looked at that, or I don't remember. I know there's 5 volt and 3.3 volt on here, but so on this thing. So, but we need to look on the schematic if it's using mostly 3.3 volt or mostly 5 volt because there's some down converters on this board. I know there is a converter here, but I believe that's for the backlight. And there's an inductor here, so that might be converting something. So we'll need to look at the schematics of this thing, if it needs mostly 3.3 volt and a little bit of 5 volt, or if it needs mostly 5 volt and then makes its own 3.3 volt, because that's going to influence what we're going to make to feed this and the rest of our electronics, right? So we could make 5 volt and then have an LDO for 3.3 volt. That gives a nice clean output, and that's a very little drop, so that's pretty easy to do. Or we could straight go to 3.3 volt and then boost if we only need a little bit of 5 volt, maybe somewhere. Yeah, we'll have to see about that. Okay. Yeah, let's save that. We kind of landed at the point where we wanted to be. I cheated a little bit with the buck converter, but as I said, we'll go more into this in the next stream, or we'll repeat that, and then that should make sense too. This is just one I've been using for a different project already, so I thought I'd use it again because it's really cheap and small. And it has some EMI stuff in there. It depends on what you need most. If I need 3.3 volt the most and I only need a bit of 5 volt, it's easy. I can just boost a little bit of 5 volt instead of making everything 3.3 volt and then burning it all through an LDO. Instead of making 5 volt and then burning it off to 3.3 volt, well, we need like 500 milliamp. That's going to cost a lot more, or a lot more heat and efficiency at least, right? And these things are going to be running 24/7, so a little bit of efficiency would be nice. So it all depends if we need 3.3 volt most or 5 volt most. And then we'll generate that and then either LDO or boost. Doesn't the display board handle that based on input? Well, this one can run from USB. So I have the suspicion that the 5 volt to 3.3 volt is on here. So that if we feed it 3.3 volt, there is a 3.3 volt pin. I think the 3.3 volt pin here is an output to the board it's going to connect to, and not an input. So I think this board needs 5 volt because it has USB-C, which is also 5 volt, and then it makes its own 3.3 volt. But yeah, we need to look at the schematics and then we'll see. If it does, then we'll have the buck converter make 5 volt, and then we won't use its 3.3 volt. We'll make our own 3.3 volt on the board we're designing for that board and the sensors and things like that. But yeah, we'll check that in the next stream where we dig into that datasheet, and we can pretty easily find how that's all connected. And I mean, it has to basically make its own 3.3 volt, because otherwise it would only have 5 and then it would never work, right? So, yeah. So probably need to go to 5 volt, but in regards to this, that is just a resistor change here, and, oh well, probably also capacitor change, because then 10 volt capacitors aren't great because of the derating. So, yeah. Cool. Well, another slow live stream, but I hope somewhat informative. We finally got past the stupid transformer hurdle by still not having a transformer, because we basically couldn't find any in stock. So I'll have to use my contacts to see if I can maybe order, like, I don't know, 20 or 30 of those, and then have them delivered to JLC PCB where I'll do the prototyping. And yeah. Oh, secrets! Secrets! Yes, sure. Let me close this, and this, and this, and this, and then go here, and then close that. There we go. This week, I received a new prototype for the DigQuad V4, And the previous prototypes, although they all worked perfectly, I did some lab testing on them, and while I could get them to pass with some tricks, let's call it that, I didn't like the results. I didn't find them good enough. So I redesigned the DC-DC stage on here, and I used a new buck converter and boost converter. And I had to change a lot on the ESP32 module. I removed the buck converter on here because it was just generating too much noise. And I went back to an LDO, but I separated the LDOs for the Ethernet and the ESP32. So there's two LDOs on there. And I made it even more intelligent. It can basically now auto switch between 3.3 volt sources and 5 volt sources. So if I connect, I don't know, 3.3 volt, you'll see an LED light up here next to VBus. So it knows that it's VBus in, and that it doesn't have a 3.3 volt source from the board below it, this guy. So it now makes its own 3.3 volt for the ESP and for the Ethernet. And, well, does all its things, that's fine. But if I plug it into this board, which actually provides it 3.3 volt, the onboard 3.3 volt logic is, or LDOs are disabled, and it now gets 3.3 volt from this baseboard. So the LDOs basically turn off and it becomes more efficient. And I hope that also solves my EMI problem. There are some small issues I needed to solve, like I didn't really take into account that this USB port would be here and this large capacitor would be here. Now, in the end product, the ESP32 with Ethernet is going to sit higher like this. And then it's actually not a problem, but I've made a revised version where I move this capacitor to the left, and then it's never going to be a problem. It's not a problem now, but it's like, you know, too close to comfort. Or for comfort, right? Yeah. So yeah, there's some other improvements for the DIG quad. It now gets a 2 pin VEXT input, so just positive and negative, and then gets the same relay output the DIG Next has. So you just connect the included cable to your relay board like that, and you just have plus and minus from a second supply there, and voila, you have your relay functionality enabled. No more double splicing wires and all kinds of other crap. I thought that was a nice solution. We now also have an I2C port over here, which actually has the RX and TX pins on there if you want to troubleshoot with an external IC. We have the new style fuses on there, reverse polarity protections, ESD protection is a big new one. We have ESD protection on the in and outputs for the power, and separately on all the data lines. It's not the circuit of the DIG Next. The DIG Next goes further with ESD protection, but also over voltage protection. That this one does not get. We still also have the resistor switcher. The DIG Next has a different circuit on there, but I thought it'd be nice to keep the resistor switcher on here. Yeah, and it's all out, you know, completely redone and renewed DIG quad without changing anything about the physical layout. So all the screw terminals and all the pins and everything else are still in the exact same spot. So cases and other things should still fit, right? And they'll come with these new ESP32s. And yeah, I've been working on those. Sadly, this one did everything correctly. And even the most complicated circuits worked perfectly. But the boost converter I used on here is a piece of trash. It basically gives you 4.9 to 5.3 volts or anything in between. Yeah, and they kind of hid it in the datasheet that would be the tolerances, but it turned out that those were the tolerances, and that's in spec for them. Well, not for me. So Yeah, I have to do another prototype run, but hopefully that is basically that is the only fix I needed to do. Other tests worked great, and hopefully the new selected boost converter does what I wanted to, and then we're going to be able to bring this out really soon. It's still a month or 1.5 or 2 away before we actually have the production done then, but yeah, well, we're going to see. Yeah, so I was hoping this was done, but yeah, then the boost converter kind of screwed me. Yep. So yeah, hopefully that solves all the lab issues I was having, because functionally everything worked great. It just made a little bit more noise than I'd like. So yeah, then I'd rather have them CE certifiable than not. So yeah, 1.5 to 2 months, I hope that we'll have them available, but I can't guarantee anything yet. So even if you draw all the circuits perfectly, it still doesn't mean it'll work out perfectly. Okay. It is now... Oh, what? It is now 29 degrees in this room because of the computer and all the screens and things like that. I'm going to go. I thank you all very much for watching and joining me along in my wall panel design series tutorial PCB whatever adventure, and I hope to see you back next time, which will either be a video or another live stream, and we'll continue this. Thanks for watching, guys. Bye bye.